Hi again, good to see you. In this video we examine a method allowing us to approximate values for areas and volumes of shapes, all related to function curves. The topic leads to the major and very important area of calculus called integration, sometimes anti-differentiation. The trapezoidal rule is a technique used to obtain an approximation to an area or a volume. The area might be shown in a sketch or in a photograph. For example, we might have to estimate the area of the Curl Lagoon shown in this magnificent photograph. Alternatively, the area might be that under a mathematical curve as that shown on the right in the shaded region. If you are doing a course involving calculus, then the exact value of an area is generally calculated as a definite integral rather than using an approximation method like the trapezoidal rule. You can find the details and techniques of integral calculus in a separate section of this website. Either go via the main menu or use the index and go under C. There are actually at least two commonly used approximation methods for finding areas and volumes. One is the trapezoidal rule we're going to address here, and the other is the Simpson's rule. Both provide a quick yet approximate value to solve a relevant problem. The approach I use to determining the area of a trapezium is covered in a video elsewhere on this site. Go to the index and look under trapezium. That approach is a bit different to the traditional approach in that I consider the concept of what we're doing as important, not just accept a basic formula. So you should review that video. In essence, what I'm saying is that if we have a trapezium as shown, and we put the measurements in, and we say the measurement of the top parallel side is A units, the measurement of the bottom is B units, and the height and the distance between them is H units, then we can chop the triangles off the bottom parts and put them into the top parts, and then we form a rectangle. And the length of the side of the rectangle is simply the sum of the parallel sides divided by 2. Consequently, the area of a trapezium can be regarded as being half of the sum of the parallel sides of the trapezium times the distance between them. To demonstrate how we apply the trapezoidal rule to the area under a curve, let's have a curve which is y equals fx, and we have a line drawn at x equals a, and the height of that line is of course fa, and we have a line at b with the height of that line being fb. We can then see the region under the curve between x equals a and x equals b has now been shaded. It is a trapezoidal rule, so we need a trapezium. So I'm just going to draw that black line between the two red lines so that we can see where we're going. Now the vertical red lines are going to be the parallel lines in the trapezium, and the distance between the points A and B along the x-axis is going to be the height of the trapezium. So we've got a trapezium on its side basically. So now I'll get rid of the A's and B's etc. and use real numbers. So along the x-axis I'm going to note 1 and 7, and along the y-axis we're going to have the values 2 and 9. We'll have a look at the area of the trapezium formula again, which requires half of the sum of the parallel sides times the distance between them. Well, the sums of the parallel sides are 9 and 2, 9 plus 2. So we put that in over 2 times the distance between the x values, 7 minus 1 is 6, so times 6. Simplify that and our area is 33 units squared. We notice that the area of the trapezium is a lot bigger than the area under the curve because it's an approximation method. Now, if we want to improve our accuracy, we can have two trapezia, not just one. So I've drawn the two trapezia in according to a second black line, and you can notice that the black line is much now closer to the blue line for the area under the curve. So we're going to get a better estimate. But we now need calculations for two trapezia. So I've put my values in at x equals 4, and it happens that the y value is also 4. So we've got that, and the left-hand trapezium has now parallel sides of 9 and 4 units, and the height is 3, 4 minus 1, and the right-hand trapezium has parallel sides of length 4 and 2. So we substitute into our basic formula separately for the two trapezia, and we can say it's 9 plus 4 divided by 2 to average them, and then times the distance between, which is 3, and then plus 4 plus 2, the sum of the parallel sides for the right-hand trapezium, over 2 times 3. Simplify that in the calculator, 28.5 units squared. Much less than the 33, so probably a more accurate estimate of what the real area of the curve under the blue line is going to be. It's a bit of a pain having to do the two trapezia separately, so let's have a look at what we've just done. Now, we see that there's a common denominator in both, 2, and there's also the common width of the trapezium, 3, and we can probably factorise out those two numbers. So 3 over 2 outside of brackets, the sum of the parallel sides for the first is 9 plus 4, plus the sum of the parallel sides for the second, which is 4 plus 2. That's a bit easier. So we can rearrange our concept of the formula now to say that the area of a trapezium, when we're applying the trapezium rule, can be the difference between the x values divided by the 2 for averaging, and then simply the sum of consecutive pairs of y values. A lot easier to think about it if we do it that way. Now there's a few terms you need to know if you're going to understand the questions which are going to be asked of you in the exams. The first term is related to function values to be used and the number that you have to use. Well, the function values are simply the number of vertical uprights you need to consider. So in that last question, for example, we had 3 vertical uprights, so we had 3 function values. The other way that they can state the question is in terms of the number of subintervals or the number of trapezia to be used. And this is really the number of gaps or the number of trapezium between the starting and finishing values. Note that there is always one more function value than the number of subintervals because we have to count the first value. So let's look at that again. Here's a couple of rough old curves I prepared earlier. If we have the left-hand curve, we notice we have 1, 2, 3 function values or vertical uprights, and we have 2 subintervals or 2 trapezia. In the right-hand curve, we have 1, 2, 3, 4, 5 vertical uprights, in other words, 5 function values. And then we look at the gaps between those function values and we have 4 subintervals or 4 trapezia. So now we're going to do an example which is precisely the kind of example you're going to get in your examinations. We're going to use the trapezoidal rule to find the area between the curve y equals square root of x squared plus 9 and the x-axis between x equals 0 and x equals 4 using 3 function values. You'll always be given the limits and you'll always be told the number of function values. So always the same approach. First of all, draw up a table. Secondly, put in your x and y values in the left-hand column. Then put in the first and last of your x values. We then average those two to get the middle value. Then we calculate, using the x values, our y values, so just substituting into y equals the square root of x squared plus 9, gives us 3, root 13 and 5. Going back to our area formula, we're going to say that the difference between the x values, which in this case is 2, so write that down, over 2 for averaging, and then we have the sum of 3 plus root 13 and then the sum of root 13 plus 5. So simplifying that down, we get 8 plus 2 root 13 units squared. Leave it like that. Beautiful answer. Now in the next example we have to find the approximate area between the curve shown and the coordinate axes using three function values. The difference is that we haven't been given the equation, we've just been given the diagram, and so we have to read our values for x and y off that diagram. So following the same steps. So draw up your table, put in x and y, put in your first and last x values, which are 0 and 8, and then average to get the 4, which is what they gave us in the diagram anyway. Then the y values we just take off our graph. So at x equals 0 we have y equals 9, x equals 4 we have y equals 8, and at x equals 8 we have y equals 0. Now we think of our formula for what we want to do, and we say the difference between the x values. Now looking at our table, the difference is going to be 4 over the 2 for averaging, so we substitute into our formula for that, and then we say that we have the sum of the consecutive pairs. Well, the sum of the first two is 17 and the sum of the second two is 8, so we have 17 plus 8. Simplifying that down we get 50 units squared. So our final example is for a real life object, and this is my rock, which I use as a paperweight, and I've measured it across the width. I wanted to find its area, so I started from 0 and then with 15 centimetres wide, and then I made measurements on a regular basis, and that was every 3 centimetres. I've really got 5 sub-intervals there, and so I divided 15 by the 5, and I found it was 3 centimetres. So every 3 centimetres I was able to make some measurements. So I start the same way, draw up a table, put in my 0 and my 15, and then put in the other values based on every 3 centimetres, so 3, 6, 9, 12. I then put in my y values. The first and last ones are going to be 0 because there's no height at those two spots, and then every 3 centimetres, 8.3, 10.1, 9.7, 8.5. Now I think of my formula, which I'm going to use for my trapezoidal rule, and that says the distance between the x values, which is 3, over 2 for averaging. So I put those two values down, and then I add my consecutive pairs. So 0 plus 8.3 gives me 8.3, 8.3 plus 10.1 is 18.4, etc. So I put all that in my calculator and I get 109.8 centimetres squared. A very, very impressive rock I have for my paper. In summary, the trapezoidal rule is a method used to obtain an approximate area or volume under a defined curve or of a physical shape or region, such as a lagoon, a swimming pool, a rock or an egg. The first decision we make is about how many observations are to be made, so the number of function values. This value is given to you in an exam, but you will have to decide it for yourself if you're going to do a fancy pool or in a curvy space, or you too have a rock. After you make your measurements at regular or even intervals, always copy your results into a table. It's very important that you put them in a state that you can use easily. And then to calculate the value of the area of a successive trapezia, you simply use the formula that we're talking about, and that is that the area is equal to the difference between the x values in your table over 2 for averaging those lengths, and then the sum of consecutive pairs of y values. So you should now have the steps to apply to use the trapezoidal rule to find approximate areas and volumes under curves or for shapes within the context of calculus. Hope I've helped you to clarify the approach and the techniques. Thanks for watching this video. In the next video in the series, we look at ways to integrate functions and to find exact areas. Hit the like button and subscribe if you haven't already. Go and do some questions in Test Yourself 1 on my website, drjaysmaths.com, and then just click the back arrow from now and you'll be able to get there. Add a comment or send me an email if you have any questions. Good luck, enjoy the trapezoidal rule, look out for some rocks.